Well, I'll get started. Let me begin with a word of prayer. Heavenly Father, we thank you for this day. Again, I thank you for this class and this opportunity we have just to meet and study linear algebra together. Help us to understand a little bit more. Help us to glorify you what we do, Lord. In my prayer, Lord Jesus. Amen. So we have been studying inner product spaces, and so we've been looking at notions of what it means for things to be perpendicular, or the length of vectors in an abstract context. And so now we've reached, like, the big thing we proved last time, of course, is the fact that if you have a subspace of a finite dimensional inner product space, then we have the direct sum of W and its perp gives us the whole space, right? And we even have formulas for the projections like we looked at last time. The next section, section 6.3, which is where we are now, if I can find it, is on the adjoint. So we'll pick up there. Of a linear operator. Now, so we'll begin with a theorem, and here's how it goes. Let V be finite dimensional inner product space over a field F, all right? And let alpha be a dual vector, right? And remember what that means. What that means is that it's a linear transformation from V back to the field again, right? Then there exists unique vector, and I'm going to call it alpha sharp in V, such that alpha of x is equal to the inner product of x with alpha sharp for all x in V. All right. So I'm changing the notation from the book a little bit, but here's how it goes. Let's look at the proof. So we'll let a beta be an orthonormal basis as usual. All right. Well, I guess we could follow the proof in the book, but that seems kind of boring. Let's work it out instead. So how would we find this vector alpha sharp, right? We can solve for it, right? Let's try that. So let's call alpha sharp, the book calls it y, all right? So let's just try to work it out, see if we can figure out what it should be, just from calculation here. So how would it go? We need alpha, right, of what's the most interesting vector to look at to define something? If you got an orthonormal basis, right? we probably should use the orthonormal basis to learn things. So let's look at that. So if we look at alpha of vi, right, that should be equal to, allegedly, alpha v sub I of y, right? But what did we also know previously? Y can be written as what? The sum of what? Y with vi, right? Let me use a j here. Then did we not? We proved this last class, right? Yeah. So if I put that in, what happens then? See, I got wow, Soprano's kind of rowdy today. Let's see here. So these are constants, right? What does it cost us to pull them out? I can pull the sum out. Yeah. And what happens when I pull these constants out, though? Complex conjugate, that's right. So, and then we've got vi with vj, right? So this is a Kronecker delta, right? So what's that? What's this show me? This should be equal to what then? This simplifies simply to the complex conjugate of y with what? Not vj, but vi, right? And of course, we can use the axiom of the inner product to trade that for a what? Vi with y, if you want. I mean, I'm not sure that helps or not, but we can do that.
Don't think we really accomplished anything.
Why is that?
Because we just got back.
Oh, yeah. Oh, man. Well, that's a bummer. Well, you win some, you lose some, I suppose. Well, this is disappointing. I was trying something different for a change, and I'm once more reminded the somewhat irreducible complexity of what's in the book, you know? Rats. Well, yeah, that kind of went nowhere, didn't it? Let's see here. So what should we do? How do we find this y then if this didn't work?
Express alpha of vi.
Express this as a sum? I suppose that's true. How about this? What if we expressed the inner product? So like the inner product of x with y. Let's introduce a notation that this is, all right, so here we go. Sum over I of xi vi, sum over j of yj vj. Oh, I'm not sure if I'm really prepared to invest fully in what I'm about to do. I probably should stop, but Oh, no, I can't do this here. I'm sorry, guys. Let me stop. Rats. Fine. So what the book does, and I'm trying to derive it here, but obviously it has not happened for me today. The book says just let y equal to the sum I equals 1 to n of alpha of vi conjugate vi. Now, I think once you write that down, it's kind of like, oh, duh, you know? If I make this a j, it becomes more obvious why this works, right? So my brain not working too great today. So let's try plugging this up into there, see what happens, right? We've got vi with the sum j equals 1 to n of alpha of vj conjugate vj. So those steps that went nowhere, we're going to repeat them now, but they'll go somewhere. It's the same steps though, right? So we pull the sum out. And what happens, complex conjugate of the complex conjugate is just the number again, right? Complex conjugate, when you do it twice, it's like you didn't do it at all. And then we're left with the inner product of vi and vj. But of course that is Kronecker delta ij, which just leaves us with what? Alpha of vi, which is what we want. All right? All right, so there's that. So the interesting thing is the mapping. Alpha maps to alpha sharp, where of course this alpha sharp is, in particular, it's defined to be, you know, the sum over in our current setup. This. I do want to return to this, guys, another day. There's another way to do all this, and I was trying to get it ready for today, and I just ran out of time. But oh well. So that's the definition of this vector, and it's not immediately clear to me that that's a linear map, is it? You know, like if I had alpha plus beta, well, excuse me, the additivity is clear. I'm not sure about the homogeneity though, you know? So let me not say any more about that at the moment. It may be that this construction serves the purpose in this section in the book, but it's not the same as this looks like something else I know, but I'm not sure it's actually the same thing. So, all right, let me move on here, lest I regret my life. Moving along. So this is theorem 6.9, and it says if you have T, a linear transformation on V, all right, where V is a finite dimensional inner product space, all right, then there exists a unique T star, again a mapping from V to V linear. Why am I writing all this? I've got a notation for this. So it's a linear mapping on V, all right? Such that, and here's the deal, the inner product of T of x with y is equal to the inner product of x with T star of y. for all x and y in V. All right? And this, by definition, all right, T star is the adjoint of T. All right? So we'll go through the proof here. We let y be an element of V. All right, define alpha of x as equal to t of x comma y. All right, so y is fixed in this argument, and this is for all x in V. All right. So we can show that this alpha is linear. Let's do that. So if we look at alpha of, let's say, cx plus z, right? Then by definition, that's the inner product of t of cx plus z, comma y, right? But since t is linear, we've got c t of x plus t of z, right? T is linear. And then by the properties of the inner product, we can pull the constant out. And what do we got? Well, we've got, by definition, C alpha of x plus alpha of y, right? So therefore, alpha is an element of, the dual space to V, isn't it? Do you guys agree? Is alpha a dual vector? What's its input? A vector. What's its output? A scalar, right? Because the inner product is a scalar. So alpha is a dual vector because it's a linear mapping from V to the field of V. So then what? Well, then we appeal to the previous theorem that I almost proved. Okay? And so what's that mean? What's the previous theorem give me? Gives me a formula. Yeah. Well, it gives me a formula for y. let me follow my notes, otherwise I'll get in trouble. So yeah, so we can select y prime, an element of V, right? Unique. For which what? Alpha of x equals to what? The inner product of x with y prime, right? So how should I define T star? T star of y should be equal to what? Y prime, yeah. That's a function because y prime is uniquely assigned in this context, right? If I hadn't muddled the proof of the previous theorem, we'd have proved that already, all right? So, great. And notice then that does what you want, right? Because
T star is linear?
We haven't proved that yet, but so that would at least give us this, right? T of x, y is equal to what? X, T star y, right?
Isn't t star of 0 equal to y prime?
Hmm?
Isn't t star of 0 equal to y prime rather than being equal to 0?
Well, what is t star of 0 depends on all of this. So, you know, I mean, t star of 0 doesn't come, it comes with strings attached. It's based on this thing here, you know. It's born of the alpha that we've already defined.
But y prime is a constant, right? Or a constant for that alpha?
It's a constant for that alpha, yeah. But that alpha is related to both t and y. The given t and the given y. But we'll prove t's linear. We'll prove t star is linear. Just give me a second here. That's the next thing to do. That's the next part of the proof. So if we look at y1 and y2 in V and C in the field, if we look at X with T dual, T adjoint acting on CY1 plus Y2. I mean, at the moment, we just know that it's a function. We don't know anything else more about it. Then this is equal to, by construction of T dual, I mean, the destruction of T star, this is equal to T of X, CY1 plus Y2, all right? Which then is equal to C bar T of X, Y1 plus T of X, Y2, using the additivity and conjugate, sort of the conjugate linearity of the second slot there. And then we use the definition of T star again to shift it back. So we've got C bar X, X comma T star Y1 plus X T star Y2. And then we can bring the C back inside. I should have done that in the last step. Let me do it back here. There we go. Okay. Yeah. And then that gives me that X comma C T star Y1 plus T star Y2, like that, for all X in V, right? But one of the properties we have of the inner product is a cancellation property. If we have, X inner product with a vector is equal to X inner product with this vector, and that's true for all X, that implies that T star of CY1 plus Y2 is equal to C T star Y1 plus T star Y2. So in fact, yes, the adjoint is linear. All right. So now I guess it does technically remain to show that it's unique. So if you had, if you had another, let's see here. What if we also had T of X, Y is equal to X with U of Y, which is probably part of what you're worried about, Josh, right?
No, I misunderstood the definition of T star.
Oh.
There.
Oh, okay, good. So this would then be equal to, of course, X with T star Y, right? And again, since this holds for all X in V, that would imply that U of Y is equal to T star Y, which proves that any adjoint that we define in the way that we did, it's necessarily unique. If we could somehow find another one that satisfies the defining identity, essentially, this is the defining identity, right? This is what makes the adjoint the adjoint. So, okay, great. Now, So the adjoint is a linear transformation. And the question is then, how is it related to my original linear transformation, right? So now we also introduced the star notation just for taking the, what was it, the conjugate transpose of a matrix, remember that? So let's see, what would the matrix of the adjoint of T look like with respect to an orthonormal basis beta? How do we if we wanted to calculate the ijth component of that, how does that go? You guys remind me, what was our theorem for an orthonormal basis? And we want to calculate like the ijth component of the matrix. How do we do that? What was the formula? We do what? We do T. Was it T of VI with VJ? Was that it? I can't remember. Or did I? Is it the other way?
VJ with VI.
VJ with VI. What was that? That's section 1. I have to be careful because I'm so used to the world of real linear algebra where the order of the inner product doesn't matter. It's sort of made me numb to appreciate the order of things. But it really, really matters here because the second and the first slot are different. You know, they're different. And so what you said that it was, what did you just tell me, Josh?
T of VJ, comma VI.
So I just gotta, yeah, that always bothers me, but that is how it is. Okay, so likewise here, right? We have to do what? We have to do T star of VJ, all right, with VI. Okay. And at this point, I'm in a little bit of trouble because I forgot to prove a lemma. Right? What's the lemma I should have proved first?
That y comma t of x equals t star of y comma x, or in the brackets for the.
So yeah, I mean, we might be saying the same thing, but what I want to say is this: T star star is T. How could we prove that? What's that? Yeah, I think use the definition maybe. So if we look at, let's do x with t star star of y, right? And we'll subtract x with t star of y, not t star, t of y. What's that give us? Oh, that gives me trouble. So it gives me. Oh man, I have found a way to make that unproductive. So here, I guess to be clear, I need t star star is, how's that defined? I mean t star star. So Sam already sees it. I'm kind of brain dead. So what should I write down?
You could let t star equal g and then take a t star.
So let this be g, but how does that help me?
And then you could apply the definition of g star.
So g, oh, you're saying g of x, y would be equal to x g star y? Like that? But that would tell me that t star of x comma y is equal to x comma t star star of y. flip it and take the conjugate. That sounds like a profitable idea. All right, so that didn't work, right? I mean, I'm not saying it didn't work. It just, I guess I gotta say it didn't work. Let's see here. Well, all right. We're going to assume this for now. We're going to come back to it, okay? So this is true. It's actually not hard to prove. I'm just blanking at the moment. So if we know that, use the property of the adjoint. What do we got here? We've got T of Vj, right? And then T star star of Vi, right? But that, by the lemma that we've not proved yet, but we will, is Vi, right? Actually, wait a minute. I think I did something wrong, didn't I? So help me out. Tell me where I'm wrong, Josh. Yeah, everything I say today is garbage, pretty much. So I blame the CFARs. It's all you guys' fault. When you guys aren't here, I don't make mistakes. Just so you know. Yeah. Oh no.
T of the I on the bottom.
I was about to say, so it's always the identity. Interesting. Yeah, so T of Vi. Thank you. All right, great. Now, that's still not quite the original matrix, which is good because it isn't the original matrix, but notice that this, if we were to, we could put a complex conjugate over here, right? And then we'd have T of Vi, comma Vj, right? Which has, notice that has the I and the J roles reversed, right? So what is this? This is the matrix of T with respect to the beta basis, right? Transposed, complex conjugated, the ijth component of that. Right? So in short, the theorem that we will eventually prove once I get my act together is that the matrix of the adjoint is simply the matrix adjointed. So this is the linear transformation adjoint. This is the matrix adjoint. Remember we defined this previously? Like A star, what was it? It was A conjugate transpose. Remember that? Yeah.
And is a conjugate just where all the entries are complex conjugate?
That's right. A conjugate. So like A conjugate, the ijth component is Aij conjugate for all ij. Yeah, the component y is complex conjugate. All right, so moving along here, believe it or not, we should define,
Lemma?
what's that?
Proof lemma?
Prove the lemma.
I think if you just take the conjugate of what we had before and try to make it works. Because we had that identity go backwards. So like the first entries were second entries. So if we switch it and conjugate it both sides.
So you think I just, all I need to do is take the definition and conjugate it? Like the defining property? So if I start with like T star of x comma y equal to, what is it? X T double star y, like that. That's, all right. Then you're saying take that complex, so you guys got the This is actually the bigger point, but I'm going to erase the large point to go back to the lemma. All right, so complex conjugate both sides, you said? Then what does that do for me?
And then you can simplify that by flipping the first.
So I got y t star x equals to the, just leave this alone?
If you change that side to it, you get back, well, x and y, it's get back, t of x.
So what was I supposed to, did I do it wrong?
Yeah, I think I see what he's doing. Just with the spot that you have the complex conjugate.
So not on both sides, just two of them here, yeah?
No, you do it to both sides.
All right.
And then down there, because you're taking the complex conjugate of x.
So you want me to get rid of this and flip them?
Yeah.
All right.
But we know that the left side is equal to t of y comma x.
Right.
So we've shown that t of y comma x is equal to t double star of y comma x.
So this holds for all v. So therefore, yeah, very good, guys. You got it. I think this might have been a homework problem. So, but I would say, by the way, like, you know, as I look at this section and I'm looking for like future test questions, I think pretty much all of the properties of the adjoint, these are actually pretty good test questions. You know, don't mistake my. I can't do anything today. I just got stuck on something in physics. So, you know, I wouldn't make too much of me not being able to do something here at the moment. Okay, so what is the point? You know, we can calculate this adjoint. It's unique. Its matrix is the conjugate transpose. But the next section actually shows us what we're actually after here, guys. For one thing it does is the first lemma is if t is a linear operator on a finite dimensional inner product space, if t has an eigenvector, then so does its adjoint. Let's look at that. So if t has an eigenvector, so does its adjoint. So, okay, first of all, some of this I'm more used to. Let me explain to you what this is. In some sense, generalizing, like if we have a complex eigenvector, right, then it's got a complex conjugate eigenvector, right? I feel like this lemma is in some sense a generalization of that idea. And it's quite beautiful how it works, this lemma. Let's look at it. So we're in 6.4 here. First lemma in section 6.4. It says if you have t, a linear operator on a finite dimensional vector space, inner product space. All right, if t has eigenvector, then so does its adjoint. All right, so let's look at the proof of this. All right. So proof. Here we go. So we're going to let v be the eigenvector of t. We'll suppose t of v is equal to lambda v, where v not equals to 0 and lambda is some number in the field, right? And then this check this out. For any x in v, all right, 0 is equal to 0 with x. We agree? Right? You can't disagree with that. What's up next? Well, we can rewrite 0 as, oh, I see. T minus lambda, right, times V, right? Because that's 0. Now we can use the adjoint construction, right? The adjoint basically gives us license. So like, once we're done working out all the properties of the adjoint properly, and I can actually think again, basically all that happens is if you move a linear operator from one side to the other of the inner product, it just adds a star. You can just look at it. It's star is going this way, star is going that way. And it's also such that star is, that cancels out, right? Like that's basically all that happens. So anyway, this gives me V with T minus lambda adjoint acting on X. So what does this say? So I guess I should mention, once you work out things here, that works out to the adjoint of T minus lambda conjugate acting on X, okay? So the adjoint of a scalar multiple of the identity is just the complex conjugate of the scalar multiple times the identity. That's how that works out. And so what do we have? It says V is in the perp. So if we look at the range of the adjoint minus lambda conjugate, right? That is a subspace of V, right? That's a subspace of V, and the big V, the whole vector space. And that little vector V is what?
Non-zero. V is non-zero,
Mm-hmm.
which means that T conjugate minus lambda, also lambda conjugate would be the term for it. But anyway, that of X is 0.
Right, but it's not in the range, right? What is it? It's in the perp, right? It's perpendicular to the range, right? But notice that it's, I mean, if this was just for some X, that'd be one thing. But it's not just some X, right? This identity holds for all X in V, right? So if you let X go over all things, then this traces out the full range, right? Everything in the range, this V is perpendicular to. So it's in the perp to the range. Right? But we also know that V is what? It's the range of T star minus lambda bar direct sum what? Right?
Direct sum of itself?
Well, I'm missing something, aren't I?
Perp?
Yeah. So where is, so if V is in the perp of, you know, so V's over here, right? All right, I'm sorry, I'm missing. He says V is orthogonal to the range of T star minus lambda, lambda bar I, so T star lambda is not onto. Okay. I guess this isn't helpful. I thought this would be helpful. Maybe it's still helpful. I don't know. But the larger point is that the range of T star minus lambda bar is not equal to the whole vector space, right? In particular, V is not in there, right? But what does that mean? What kind of operator is this? It's a linear transformation from V to V, right? So if it's not onto, that also means it's what? Not one-to-one, which means that its kernel is non-zero, right? And what does that mean? Which, by the way, is the eigenspace with respect to the adjoint map for eigenvalue lambda, right? In other words, there exists an eigenvector for the adjoint with eigenvalue lambda bar. Sorry for this detour into this business. I thought that would be helpful, but I was wrong. Okay? So, next up, we define, if I can find a spot. I guess I'll do it over here. So definition, T, a linear operator on a finite, well, it doesn't say finite dimensional here, so just an inner product space, all right? Then T is normal if T star is equal to T star T, right? Likewise, a matrix A is normal if A star is equal to A star A, right? In some sense, this is the more interesting. I don't know, there's a lot to say about the adjoint, and I haven't said yet. I've only scratched the surface so far, guys, but I'm going to skip ahead just a bit and tell you the big theorem, tell you where we're going. So the big theorem is this. T, a linear operator on a finite dimensional inner product space, all right? Then where'd it go? I'm sorry, I'm on the wrong page. No, I'm not. There we go. Then T is normal if and only if there exists an orthonormal basis of eigenvectors for T. This is the whole reason we're studying all this. I mean, at least a good part of the reason we're studying the theory here is we'd like to understand this theorem and how to prove it, because this rests at the foundation of so much of interesting applications of linear algebra, like least squares and other things. But this is it. Like, this is, so if this is the case, if the transformation is normal, we don't need all that Jordan form stuff because it's diagonalizable. Not only is it diagonalizable, it's diagonalizable with respect to a orthonormal basis. So normal operators, normal matrices are super nice. We'd like to understand their properties. So that's where we're going next class. But anyway, my apologies for all of my many sins today. So have a good weekend, guys.